In this talk, I introduce our recent work, DeepSearch. Deep neural networks are vulnerable to adversarial attacks. To evaluate adversarial robustness of neural networks in realistic scenarios, we develop black box attacks in query-limited setting. We assume that attackers have no knowledge of the target network. They can only query the network for its prediction score and have a query budget. The development of DeepSearch focuses on three aspects: feedback-directed fuzzing, iterative refinement, and hierarchical grouping. DeepSearch mainly uses feedback-directed fuzzing to find adversarial examples. Once an adversarial example is found, DeepSearch uses iterative refinement to reduce its L-infinity distance. DeepSearch further utilizes hierarchical grouping to improve its query efficiency. Here is a workflow of DeepSearch. In the rest of the talk, I will introduce DeepSearch in more details. Based on linear assumptions, DeepSearch uses feedback-directed fuzzing to effectively mutate input images towards decision boundaries. In each iteration, DeepSearch generates mutated images through syntactic linear perturbation. After querying the neural networks on mutated images, DeepSearch synthesizes a new seed image to be used for fuzzing in the next iteration. The fuzzing process continues until it either finds adversarial examples or it reaches the query limit. I will first introduce how DeepSearch attacks binary classifiers, and then extend DeepSearch to deal with multiclass classifiers. First, let's consider the simple case of linear binary classifiers. Assume that x0 is an input image with only 2 dimensions. The region within the dash-dotted square represents the set of images within L-infinity distance d from x0. Our task here is to find an input image within the dash-dotted square that is across the decision boundary, denoted by the straight line. Input x0 has 2 coordinates for the horizontal and vertical dimensions respectively. DeepSearch independently mutates each of the 2 coordinates to the minimum and maximum values that are possible within distance d, with the intention of finding the input point where the classification function f has a minimum value. Let's first consider the horizontal dimension. By mutating the coordinates of x0 on the horizontal dimension to the maximum and minimum value bounded by L-infinity distance d, we derive 2 mutated images x1 and x2. DeepSearch evaluates f on x1 and x2 and would select the direction that causes the value of f to decrease. This is because in our example, an adversarial example must make the value of f negative. Let's assume that fx2 is less than fx1. We thus choose to move x0 towards image x2 for the horizontal dimension. Similarly, on the vertical dimension, DeepSearch generates 2 mutated images x3 and x4. Assume that fx3 is less than fx4. We thus choose to move x0 towards image x3 for the vertical dimension. By combining the coordinate for the horizontal dimension of image x2 and the coordinate for the vertical dimension of image x3, we derive x0 prime, that is across the decision boundary, which is an adversary example. Next, we will generalize DeepSearch to nonlinear binary classifiers. Since the classification function f is nonlinear, the decision boundary of f is a curve. Unlike linear binary classifiers, the nonlinear case is handled by iteratively approximating the minimum value of f within the given L-infinity distance. Starting from x0, DeepSearch treats f as linear and generates x1 exactly as it would for a linear binary classifier. Observe that x1 is not adversarial. After generating x1, DeepSearch iterates starting from x1, while again treating f as linear. As a result, we generate x2, which is adversarial. The reason we can treat nonlinear binary classifiers as linear ones is that perturbations of pixels are only allowed in a very small n-dimensional cube, constrained by the L-infinity distance. Within such a small space, we can effectively approximate nonlinear functions using iterative linear approximations. Now, I extend DeepSearch to deal with multiclass classifiers. The insight of extending our approach to multiclass classifiers is based on the following fact. That is, a multiclass classifier can be decomposed into multiple binary classifiers such that the original classifier can be reconstructed from the binary ones. This implies that a multiclass classifier has an adversarial example x if and only if this input x is also adversarial for some constituent binary classifier. More details about this can be found in our paper. Now, let's look at a simple example of attacking linear multiclass classifiers. In this example, we have three classes L1, L2, and L3. The input image x is classified as L2. The decision boundaries of two corresponding linear binary classifiers G21 and G23 are denoted as straight lines. Classifier G21 actually decides whether input images are more likely to be in class L1 or class L2. Classifier G23 actually decides whether input images are more likely to be in class L2 or class L3. In our example, both G21 and G23 classify the input image x as class L2. We can find an adversarial example for the multiclass classifier as long as we can find an adversarial example for either G21 or G23. As a result, DeepSearch attacks the two linear binary classifiers simultaneously. DeepSearch generates input x1' for function G21 and input x3' for function G23. Since x3' is an adversarial example for classifier G23, x3' is therefore also adversarial for the multiclass classifier. To deal with nonlinear multiclass classifiers, DeepSearch attacks corresponding nonlinear binary classifiers iteratively. Let's look at a simple example here. In the nonlinear case, both G21 and G23 are nonlinear binary classifiers. In the first iteration, we first evaluate the value of G21 and G23 for input x0. Assume that G21 x0 is less than G23 x0. Since G21 evaluates to a smaller value than G23 for x0, we consider it more likely to go across the decision boundary of G21. Therefore, in the first iteration, DeepSearch attacks G21. By treating G21 as linear, DeepSearch generates x1. Observe that x1 is not adversarial. In the second iteration, assume that G21 x1 is greater than G23 x1, DeepSearch attacks G23. By treating G23 as linear, DeepSearch generates x2, which is an adversarial example for both G23 and the multiclass classifier. Through feedback-directed fuzzing that I have just introduced, DeepSearch can effectively find adversarial examples. Once adversarial examples are found, DeepSearch uses iterative refinement to further reduce the L-infinity distance of adversarial examples. First, let's look at the case of linear multi-class classifiers. Assume that we have already found an adversarial example x1 at a distance d1 from the input image x0. DeepSearch first uses bisect search to find the smallest distance d, such that the projection of x1 to the region within distance d from x0 is still adversarial. In our example, this distance is d2, and x2 is derived by projecting x1 to the region represented by the inner dash dotted square. So x2 is closer to x0, which means it has a lower distortion rate than x1. Since we are using bisect search to determine distance d2, x2 is the closest adversarial input to x0 that may be generated by projecting x1 on smaller region. However, in the region within the distance d2 from x0, there may be other adversarial inputs that get us even closer to x0 with projection. To find such examples, we apply feedback-directed fuzzing of DeepSearch, starting from input x2 and search within the inner square. As a result, we generate adversarial input x3. Next, by projecting x3 to the smallest possible region around x0, we find x4 at a distance d3. Assume that we cannot find another adversarial example in the region within distance d3 from x0. Our technique returns x4 as the adversarial example with the lowest distortion rate we can find. The iterative refinement process for nonlinear multiclass classifiers is similar. Starting from an adversarial example x1, we find a closer adversarial input x2 through bisect search. Starting from x2, we find another adversarial example x3 at the same distance from x0 through feedback-directed fuzzing. Finally, we find x4 through bisect search, which is the adversarial example with the lowest distortion we can find. The iterative refinement approach of DeepSearch can effectively reduce the average distortion of adversarial examples. To improve query efficiency, DeepSearch adapts an existing hierarchical grouping strategy to our setting and can dramatically reduce query numbers for constructing successful attacks. More details about the hierarchical grouping of DeepSearch can be found in our paper. We have evaluated DeepSearch against the 4 state-of-the-art black box attacks on 3 popular datasets. The metrics we have used in our experiments are attack success rate, average distortion rate, and average queries. In our experiments, we have attacked both defended and undefended networks. Our experimental results show that DeepSearch is the most effective in attacking both defended and undefended neural networks. For example, the figures here show the success rate of various state-of-the-art black box attacks with respect to query numbers. The performance of DeepSearch is shown in the red color. As we can see, DeepSearch outperforms all other state-of-the-art black box attacks. From more detailed experimental results, we can see that DeepSearch has the highest attack success rate. DeepSearch has found adversarial examples with the lowest average L-infinity distortion rate, and DeepSearch has the highest query efficiency. Although DeepSearch is an L-infinity attack, adversarial examples found by DeepSearch also have low average L2 distortion rate. In conclusion, DeepSearch is a novel black box fuzzing technique for attacking deep neural networks. It is simple and effective. It outperforms state-of-the-art black box attacks.